Hello everyone, and thank you for attending today's webinar. My name is Abelardo Morales, and I am the Department Manager for Cable and Low Voltage here at ETAP. Cables are essential components for electrical power systems. They are the backbone of the electrical infrastructure as they power everything, from small-scale household appliances to industrial machinery, and on a larger scale, complete electrical grids. Verifying that the cable does not exceed the thermal rating is crucial as it ensures safe, normal, and reliable cable operation within the system. In addition, from a long-term perspective, it helps prolong the integrity or life of the cable by avoiding thermal damage, specifically to the insulation layer. I will be presenting cable fundamentals, and I will show you how to perform cable ampacity and sizing calculations with the tools available in ETAP to make this process easier and more efficient. Cable manufacturers and standards define base ampacity values, which are based on a particular installation conditions and specific to base temperatures. However, these installation conditions rarely reflect the actual installation and operating conditions of the cable. As a result, cable ampacity calculations need to be performed to account for such differences. The differences can be accounted through a full thermal analysis or through the use of an adjustment or correction factors. These factors are valuable as they help calculate the maximum allowable current. These factors include, but are not limited to, physical construction of the cable, such as the conductor material, diameter, layers, and thickness of the insulation, armor, sheath, bedding, etc. Location and installation of the cable, underground or above ground conduits, trays, cable formation and spacing, etc. Ambient temperature as it directly affects the heat dissipation, grouping, the quantity of cables, effect of the thermal sources such as steam pipes, thermal insulation, harmonics, which cause additional rise in temperature, solar radiation, and additional adjustment factor. On the cable sizing side, there are also many constraints to consider which impact the size of the cable. These include loading, voltage drop, short circuit, minimum starting voltage, and overload, to name just a few. So, as you may have realized, there is an extensive amount of work to be done for this analysis, as many factors need to be considered to determine the cable's proper size so that its thermal limits are not violated, which in turn ensures normal and reliable operation. In this webinar, we'll go over the various calculation tools to streamline the cable ampacity and sizing calculation process through the use of specialized tools available in ETAP. In this presentation, we will be taking a look at the different ampacity methods and standards, cable ampacity calculation and setup, phase or line conductor sizing and setup, cable manager, reports and deliverables, and then we will summarize what we have learned. I will begin this presentation with an explanation of cable ampacity analysis and why is it necessary to perform such analysis. Cable ampacity is also referred to as current carrying capacity in IEC, refers to the maximum current a conductor can carry under the conditions of use without exceeding its temperature rating. Essentially, the analysis considers the cable thermal limits according to the operating conditions. Since the project I will be using in this presentation is an English 60 Hz project, I will refer to the current carrying capacity as ampacity. ETAP offers two calculation methods, the thermal analysis method and the standard-based. Let's explore both of these. Thermal analysis is a full analysis calculation method, and it is the most comprehensive method of the two methods you see here. Due to its ability to assess the thermal behavior of electrical cables and a wider range of considerations, it is considered a calculation-intensive method. In ETAP, the available thermal calculations method for thermal analysis include Near-McGrath method, the calculation method provided in IEC 60287 standard, and finite element method, which handles more complex scenarios, incorporating a flexible and detailed approach. In ETAP, both the thermal analysis calculation method and the standards-based option are applicable to underground duct banks and direct buried cable installations. Let's go over the features in ETAP and then demonstrate an example. In ETAP, if we switch to the Cable Systems group, we can access the underground raceway systems. Here, we can create new systems, modify existing ones, or run thermal analysis. If we go to the presentations, we can see that there are two existing presentations. The first one is for the direct buried presentation, modeling cables directly buried underground. The second one is a duct bank presentation, which models an underground duct bank with cables installed in PVC conduits. To make modifications to this presentation, we need to make sure we are in edit mode. ETAP provides flexibility in this process. It models the location of components graphically or through data entry. The graphical process involves selecting and moving the element. If we select conduit 4 and move it to a different location, a graphical ruler appears to assist us with the relocation of this conduit. The data entry process involves specifying the data directly into the component editor. If we double-click on the same conduit, we can specify data pertaining to this conduit. Let's relocate this conduit to its previous location by entering 24.7 inches for the horizontal direction and 14.6 inches in the vertical. The conduit is relocated to its original location. The top toolbar contains display and alignment tools to assist us in the modeling process. If we click on the dimensional drop-down list, we can view the center-to-center spacing between the conduits, the edge-to-edge spacing, or both sets of spacings. Now, let's use the alignment tools. If we select conduit 1, conduit 2, and conduit 8, we can align the conduits horizontally to the top, to the bottom of a reference element. The right-hand side UGS toolbar allows me to add components to the system. We can select the Add New Cable and drag and drop to the conduit 4. We can also use an existing cable which already exists in the one-line diagram. This can be done by going to the one-line diagram, selecting the desired cable, cable 2, clicking the Shift button, and simultaneously dragging and dropping into conduit 3 of the UGS presentation. And now, this OLV cable is also part of the underground raceway system. Heat sources can also be simulated in UGS by simply selecting a heat source and dragging and dropping it into the desired location. In this case, the default temperature of the heat source is 100 degrees Celsius. However, like any other parameter, this value can be changed in the editor. Now that we have covered some of the modeling, let's dive into a calculation example. Let's click on the Cable System group once again to enable the analysis mode. In the study case, we can define the calculation method. Let's continue using the linear McGrath method. This method offers several calculation options, such as steady-state temperature calculation, uniform ampacity, uniform temperature, cable sizing, and transient temperature calculation. I would like to return to the steady-state temperature calculation. However, prior to this, we need to specify the cable's operating current. Let's open cable 2 and go to the loading page. Here, the loading current is defined in the operating amp field. This value can be user-defined or updated based on load flow results. As we can see in this example, the value has already been updated based on the load flow results which I had previously run. Now, let's run the steady-state temperature calculation. The calculation determines the temperature of this cable to be 97 degrees based on an operating current of 271.3 amps. As can be seen, having these features and solutions consolidated within the same software is one of the many advantages of ETAP, making ETAP software a one-stop solution. Due to time constraints, we will cover the thermal analysis and underground raceway systems in more details in a separate presentation. The standard-based method is also referred to as table-based method because it uses the cable's base ampacity and the rating factors to account for the actual installation condition. Base ampacity tables and correction factors are provided by the standard, typically in a table-based format. To determine the derated ampacity of the cable, the base ampacity is multiplied by all applicable adjustment factors. The adjustment factors include ambient temperature, conductor temperature, derating factors for ambient and conductor temperature, which are globally applicable to all types of installations, underground as well as above-ground installations, soil thermal resistivity, which is applicable to underground installations, grouping effect, thermal insulation, fire protection, harmonics, solar radiation, and many others. ETAP also provides consideration for any additional adjustment factor through the ability to enter a user-defined factor. The rest of the standards supported in ETAP follow this table-based method. In ETAP, these standards can be categorized into two sections, based on the voltage levels. The first section is composed of standards which support low-voltage installations. These include IEEE American Standards, IEEE 399, NEC, ICA P54440, and international standards which are applicable to low voltage levels equal to or less than 1 kV AC or voltages less than or equal to 1.5 kV DC, including IEC 6364, BS 7671, IEC 60092, National French Standard NFC 15-100, Australian and New Zealand 3008 standards, and German VDE 0298-4 standard, which is a new standard provided in ETAP 2026. The second section is composed of standards which support medium voltage installations. These include IEEE American Standards, IEEE 399, ICA P54440, NEC, and international standards IEC 60502, IEC 60092, and National French Standard NFC 13-200 standard. Let's take a closer look at the wide range of above-ground and underground installation methods available in ETAP. With this in mind, let's return to ETAP and take a look at the required setup to perform cable ampacity calculations. Since we are no longer going to be running thermal analysis, let's use the cable editor, where ampacity calculations are performed for these standards. Let's open cable 14. First, we have to define the properties of the cable. We can easily do this by clicking on the Library button. In this editor, we can select a model from the comprehensive list of models. Let's look at the characteristics of the current selected cable. This cable is a single-core copper conductor cable with a voltage rating of 600 volts. Since I want to analyze low-voltage cable installations for this example, we can continue using this cable. However, let's change the size. Next, we need to define the length of the cable. Let's define the length of the cable to be 150 feet. Now, we can move to the ampacity. Here, we can define the standard, the installation, and the actual operating conditions. Let's change the standard to NEC. If we click on the installation type drop-down list, we can see the different installation types supported by NEC. The base ampacity values are according to tables provided in Article 310 of the standard. Let's select the above-ground trace installation type For this installation, we can consider adjustments for the tray having a top cover, if the cables are installed so that fixed spacing is maintained between the cables, and whether the installation is exposed directly to sunlight. If we select the top cover, the derated ampacity is reduced to 156 amps. If we select exposed directly to sunlight, the derated ampacity is further reduced. We can make use of the correction factors button. Here we can see a list of individual adjustment factors and the total factor applied to this installation. Now, let's look at the international standards. Since we are working with international standards, let's select a metric low voltage cable from the library. Using the built-in filters, let's filter by metric unit, 1000 volt rated cable, single conductor, XLP insulation, item 690, and select size 50 mm squared. After selecting the model, the editor is populated with the cable properties from the library. Now, let's look at the international standards. We have the option to choose from IEC 60364, BS 7671, NFC 15100, Australian 3008, IEC 60092, and New Zealand 3008. Let's select IEC 60364 standard. Based on the installation type drop-down list, we can see that this standard covers a wider range and more specific installation types. As there are many more installation options to choose from, such as underground duct, underground buried, embedded direct, above ground trays, brackets, ladder, wire mesh, and many others. Let's continue using the above ground tray installation. Notice that an additional subtype selection is available. From this selection, we can choose from unperforated or perforated cable trays. If we compare the base ampacity between the unperforated tray and perforated tray installation, we can see that the base ampacity for the perforated tray option is higher due to more airflow through the tray perforations, allowing faster heat dissipation. Also, for this installation, there are more layout options available for the perforated tray installation. These options include the cable arrangement, flat or trefoil, which is also known as triplex, the option to specify if the cables are touching or spaced, the number of trays, and whether the trays are laid out in a horizontal or vertical layout. Notice that in the box at the bottom of the editor, ETAP also provides informative messages to assist during the setup process or to inform of any conditions. Alright, assuming that these are the installation conditions, we have completed the ampacity calculation setup, and we can move on to performing phase or line conductor sizing. We can perform phase or line conductor sizing calculations in the sizing phase page of the cable editor. First, we need to define the cable constraints for sizing the cable. These include loading, maximum voltage drop, short circuit, overload, zero sequence, triple harmonics, minimum number of conductors per phase, and others. Let's cover 3 of the most common constraints. In the loading constraint, we can view the loading current for which we want to size our cable to be based on. This current can be specified in the loading page in the loading current for sizing section. In this section, there are three options to choose from. Operating current. This option is based on the operating current, which, as previously discussed, can be user-defined or updated based on load flow result. The FLA of element option, which is based on the full load current of an element in the system. In this case, the full load is based on CB31, which is the circuit breaker connected upstream of this cable. However, you can select any other devices available in the drop-down list, such as fuses, loads, motors, etc. If we want to enter a particular value, a user-defined value option is also available. Let's continue sizing the cable using the operating current option. Let's switch back to the sizing phase page. Now that we have defined the loading constraint, we can proceed to specifying the maximum allowed voltage drop. By default, the voltage drop value is set to 2% of base kV. For reference, E provides a max length. This value represents the maximum length that the currently selected cable can have and still be within the 2% voltage drop. Any length greater than this will cause the cable to experience a voltage drop greater than 2%. Now, based on these two constraints, let's look at the sizing results. In the results section, the optimal size consists of one conductor per phase of size 70 mm squared. The 273 amps, it's the maximum current this cable can carry as per the specified conditions we previously defined in the Ampacity page. Also, this cable will have a voltage drop of 1.38%. We can see this optimal cable size meets the loading and maximum voltage drop constraints. Let's set up the short circuit constraint by enabling the option. We can see that the parameters pertaining to this constraint are populated. Where are these defined? These values are defined in the protection page. Here, we can see all of the fault currents. These currents can be user-defined or calculated and updated based on results from star short circuit analysis. The fault clearing time is updated based on the overcurrent protected device selection. In this case, I have selected CB31 to serve as the protective device for this cable. Based on the clearing current characteristics of this breaker, the combination of the fault current and time, which produce the highest energy I squared T, is automatically determined. The fault current and clearing time are also displayed. These values are then used for sizing the phase conductor. With this set of information, the minimum cable size is calculated based on the short circuit current and fault clearing time determined from the protection page. In this particular example, if we uncheck the loading constraint, we can see that the nominating constraint which determines the optimal size is the loading constraint. In a similar fashion, we can select additional constraints which we want to consider for sizing this cable. Assuming we have selected the applicable constraints, we have now determined the appropriate size. We can go ahead and select to update this cable based on the optimal size by clicking on the Select button. The size will be updated along with the relevant data and calculations. Now, let's go ahead and look at this task on a larger scale. I need to size all other cables in my system. For this, I can make use of the Cable Manager. To access the manager, we go to the main menu bar, select Project, and click on the Cable Manager icon. The Cable Manager is a powerful and useful analysis tool in which I can view all the cables, related information, and calculation contained in the entire project in a consolidated view. This tool can assist in analyzing all the cables within the project. On the left-hand side section of the editor, there is a set of filters. I can go ahead and filter cables by connection, AC, DC, three-phase, and single-phase cables, by voltage level, even by cable types, branch, equipment, etc. The cable manager is set up so that it has pages similar to the ones of the cable editor. The data pertaining to each cable is populated in each page of the cable manager. In the info page, for example, we can view basic cable information, from to element cable connection, length of the cable, and the cable's library information. In the physical page, we can view data pertaining to the physical construction of the cable. In the impedance page, we can view the cable's impedance information. In the configuration page, we can view data related to the main cable as well as auxiliary cables. In the Ampacity page, information pertaining to the Ampacity page of the cable is reported, such as base ampacity, standard, installation type, base and operating temperatures, allowable, operating, and derated current, and even derating factors. Each page is equipped to flag for violation conditions, such as the ones we see here flagged in red. If we go to the sizing phase page, we can see that there are many properties also flagged in red. Let's move on to generating reports. Reports can be generated at an individual basis or globally. To globally generate reports, we can select multiple cables, or if we want to generate reports for all the cables in the list, we can click on Select All, and then click on Report. Provide a report name. Let's name this report Cable Sizing Report. Next, we select the type of reports to create. Let's create ampacity and sizing phase reports in PDF format. As you can see, both sets of reports have been created for all of the selected cables. We can also export the entire contents of this editor into an Excel report. With the cable selected, we can click on Export. I will name this report Global Cable Report. Our report is created and automatically opened in Excel. Navigating through each of the tabs, we can see that the data has been exported according to each page of the cable manager. Let's summarize this examination of cable ampacity and sizing calculations using ETAP. Cables are essential components of electrical systems as they provide power to almost any electrical component, from basic appliances to industrial machinery, and also within complete electrical grids. We also know that performing cable ampacity and cable sizing analysis is crucial, since using the proper cable size ensures normal, proper, and reliable cable operation of the system. We also know that there is an extensive amount of work involved in this analysis, and that is traditionally a very time-consuming undertaking. ETAP offers a suite of solutions to engineers to support these tasks, and best of all is that they are all fully integrated, saving time and ensuring compliance with applicable standards. The ETAP cable ampacity and cable sizing tools and methods include a full thermal analysis module analyzing underground cable installations, cable ampacity and cable sizing calculations for low voltage and medium voltage installations based on various standards. The Cable Manager is a powerful analysis tool in which all the cables in the system are consolidated into a single editor in the list view. Finally, ETAP offers robust report generation capability in which cable reports can be generated through a click of a button and exported into a consolidated spreadsheet. I hope you found this presentation useful and that the tools presented today can assist you in performing cable ampacity and sizing analysis more efficiently in your projects.